Morning, everyone. Welcome to this week's IQS seminar. We're glad to have Professor Eli Levenson-Falk with us from University of Southern California. He did his bachelor's from Harvard University and master's from UC Berkeley. He worked with Irfan Siddiqui for his PhD. After that, he joined Stanford for his postdoc. And since 2017, he's an assistant professor at USC. And recently, he was also joined the appointed assistant professor in electrical and computer engineering department at USC. So basically, he works on superconducting electrical circuits, and we'll be hearing about beating the Ramsey limit on sensing with Hamiltonian control. So the floor is yours.
Thanks everybody for coming. So I do all my work on superconducting qubits, and everything that is an experimental measurement here will be superconducting qubit. But this talk is really not going to be at all specific to superconducting qubits. It's going to be about a very general technique. It just so happened that that was the system we had around to test with. So first, as always, I have to acknowledge people who did all the work, most notably students Leda Hecht, who's in my lab, and Saurav, who's in Daniel Lidar's group, along with assistance from the other student, Evangelos. There's a preprint about all this if you want. It's there. But especially Melita and Saurav really did fantastic work on this. So very, very generically, let me just define quantum sensing. We want to detect some environmental quantity B. It could be magnetic field, it could be temperature, it could whatever. You want to know something. And quantum sensing is the art of making it so that your wave function depends on that. And beyond that, you're getting into specifics. However, most of the time, you're doing something that's sort of fundamentally quantum along the way. You're interfering wave functions with each other. You're entangling different things, you're making use of like single photons or squeeze states, some kind of non-classical states of light. And typically what you're doing is you're taking some system and giving it a dependence of its Hamiltonian in this environment there. In other words, you're making it so that the time evolution of the system depends on that environment. Sometimes it's a little different, but for now we'll stick. The problem is that you've made your wave function dependent on this environmental variable, but there is decoherence. And whatever your favorite model of decoherence is, I think we can all agree it's going to mess up the ability to correctly determine that dependence on this environmental variable. It's going to somehow scramble the state. So what do? Well, there's a lot of work on this. Obvious thing is just to average more. You have some limited signal and some noise, okay, average, get more signal. But sometimes you can't do that. Maybe you have a limited time window in which you're allowed to acquire your signal, either because, you just have a deadline or because the signal is going to change. You can try to make it so that your Hamiltonian depends more steeply on that signal. That's generally a problem of sensor design. You try to get your sensor to couple more strongly. I've done work on this in the past, but, it's all very specific to the sensor. It's all very, good engineering. Likewise, you can try to just reduce decoherence in the sensor. Again, often it's sensor design. Sometimes you're using techniques like dynamical decoupling to try to suppress some of the decoherence. So for instance, dynamical decoupling can be used to say, kind of lock in on a single frequency band and sort of suppress sensitivity to any environmental fluctuations that are out of that band. People have used things like feedback to start with a signal that's very, very large that might like completely saturate the detector and very quickly hone in on it to get to good precision. Some cool work from Andrew, among other people, about using weak measurement feedback to very quickly lock in on a frequency, a signal whose frequency you don't know. Some recent work from Kater Merch, who I think a lot of you know, and Nicole Herpler, looking at a signal where you didn't know what axis it was along, using weak measurement feedback. There's all sorts of like adaptive phase estimation. There's just a huge zoo of like, let's do something clever and complicated with our detection to speed things up. Now, the problem with all of that stuff is not that it doesn't work, it's just that it's hard and often requires something that your sensor may not necessarily be able to do. Like weak measurements are really nicely suited for superconducting qubits. It's pretty terribly suited for anything that's kind of dependent on a photon. It's really hard to weakly measure one photon. But there's sort of a class of problems that we can attack without having to use any extra resources. So there are problems where you have a system that you can reduce down to 2 states. So a qubit. This does generalize, but it's going to be way easier to talk about a qubit. And you say that the thing you're trying to detect is going to somehow cause a frequency shift on the qubit. It's just going to slightly change the energy splitting between the states. So we're just going to parameterize this as this detuning delta. And from now on, basically, detecting delta is the thing we're trying to do. We're going to assume that like we know this function f of b, that we know how we map the environmental variable onto delta. It's something we calibrate into our sensor. Now, detecting this is a really, really well-studied problem. Basically, in the block representation, you have a block vector representing the state which precesses around the z-axis at this detuning rate delta. That's the Larmor precession frequency. And you can detect this using the Ramsey interferometry sequence. So you're seeing the Ramsey sequence right now. It started out on the z-axis in the ground state. It got rotated down to the xy plane. Then we let it precess for a while. And then at some point, we rotate it with another 90-degree rotation back towards the z-axis, read out and get an expected delta. And this causes, an oscillatory interference signal, which goes around like this. Now, it's useful to sort of talk about this in the block representation. Again, the vector is just the expected values of the measurements along x, y, and z directions. And I am not going to write down a single density operator in this talk. We use the density operators and master equations to derive the block equations. And from then on, we're using block equations because it's way simpler. When it's come time to generalize beyond a qubit. So it's useful to look at this in just the XY projection. So this is the same block sphere. I'm just looking down from the North Pole. So perfect Ramsey sequence with no decoherence, you get this block vector and it just precesses around at a constant rate delta. And so assuming you can do some readout that tells you where in this plane it is, which is what the Ramsey sequence does, you can pick up this oscillation frequency by doing a few different measurements, and you can figure out what delta is, and that's your sensor. Now, of course, the problem is decoherence, which causes this thing to eventually shrink. So it kind of spirals and shrinks. And here what I've drawn is it's going to start over in a second, a vector where the detuning is kind of large compared to the decoherence rate. So it's spiraling around many times before it kind of vanishes. And this is a really well-studied problem. I think it's been derived pretty much how to do this optimally using phase estimation to sort of like squeeze exactly as much signal as is possible out of this. But there's another, I just wanted to mention, this is not just for quantum sensing stuff. You need to do this calibration for qubits, which is kind of why I got into this in the first place. There's another limit here, which is much harder, which is the small signal limit. So what I'm drawing here is black is the block vector, blue is the y component, red is the x component. So these are just the components of this vector. And this is the case where the detuning delta is very small compared to the decoherence rate, 1/T2. So you don't get any oscillation. It's sort of like an overdamped system. It just starts to rotate, but it shrinks. I don't know exactly why this one's going so slow, but you can kind of get the idea. Like the y here, this y component grew for a while, but then started shrinking, whereas the x component was just shrinking the whole time. And so you sort of have this competition between the growth of the y component because of this detuning and the shrinking because of the decoherence. Now, in the small signal limit, it's pretty simple. You basically have a linear growth in time because of the detuning, and then an exponential shrink because of the decoherence. Vx, basically these are just sine and cosine. In the small signal limit, Vx is pretty much constant or maybe quadratic times its decoherence exponential. Can I get this thing to restart? Nope, I cannot. Okay, so defining our problem. The goal is to detect a change in delta. And assuming delta is very, very small, and we do the decoherence rate, 1/T2, this is just going to be linearly proportional to detecting a change in Vy. So it's the same problem. So from now on, I'm just going to be concerned with detecting Vy. We need to define the SR. We need to define how hard this is. So your signal is basically, you repeat this thing n times. You do n measurements. How many times do I measure spin up along the y direction? P plus. What's that probability? N P plus is how many counts I get. In units of Vy, that's n over 2 Vy plus 1. That's my signal. My noise is the variance on that signal. If I was to do this n times, and then go and do another trial of that, and go and do another trial of that, and go and do another trial of that, what's the variance on how many counts I would get? Well, that's just given by binomial statistics. So it's just n p plus times 1 minus p plus square root. Do a little bit of math, get these Vy terms, and for small Vy, it only comes in quadratically, so you can get rid of it. And it just goes like root n over 2. So you take the signal to noise ratio, and you find it's just root n times Vy. So the more shots you get, the more SNR you get, but only sort of square root. Now, I mentioned before, you might have limited time. So let's say you have a total experimental time, capital T, and that's all you get. How many shots do you get? Well, you get big T divided by the time per shot, which we're going to say is little ti, the idle time. This is time spent doing things like preparing your state, integrating your measurement, resetting the system. This is all time where you're not really acquiring information. And then little t, which is the time that the system actually spends evolving and acquiring information. So in general, what you need to do is try to maximize Vy over root t plus ti for a given protocol. You're always going to do better by making big T longer, but we're going to assume, that's not something you have control over right now. Or maybe you can do it, but it's going to help you equally no matter what you do. So you're just trying to maximize this quantity, and I'm going to talk about it in 2 limits. In general, you're going to land somewhere between these, but the limits are easier to discuss. One is where the idle time is very large compared to the evolution time. The evolution time is probably something on the order of T2. In that case, it doesn't really matter how you set up your protocol. You're probably going to get about the same number of shots. Your idle time is just going to dominate everything. So n is going to be fixed. And so the only thing you're really trying to maximize here is Vy. On the other hand, maybe your idle time is really short. You have a very, very quick, readout and reset, and you can just spend all your time letting your qubit evolve. In that case, you need to maximize Vy over root t. So either sort of signal or signal per root time. These are going to be the quantities to maximize. And I'm just going to talk about them both in parallel. So if I was doing this for a Ramsey sequence, it's pretty easy to go and calculate the times that give you the maximum signal. This Vy is maximized at the time roughly equal to T2. Again, this is the approximation of small delta. And at that time, Vy is T2 times delta divided by E, natural log E. Vy over root T is maximized at T2 over 2. Nice little round number there. And you get root T2 over 2E times delta. So it's sort of like a very, very natural scale here. Your signal is going to scale linearly in delta. That makes sense. It's going to scale linearly in the coherence time. That makes sense. The longer your coherence, the more you can pick up. And then there's this factor of E that just kind of says okay, that's the overall prefactor. By the way, it is possible to prove that delta T2 is like the maximum signal that could ever be possibly allowed by the universe, and also probably can never be reached. So this 1 over E, it's not that bad. You're within a factor of 2.7 or so of the most you could possibly do. But we want to do better. So what I'm going to do is define these SNR enhancement ratios. So RV is going to be the ratio of VYs. For whatever protocol I do, it's VY divided by what I would have gotten for Ramsey. So this T2 delta over E. So you can think of RV here as the enhancement of SNR that I get from a given protocol in the situation where my number of shots is fixed. So it's like the SNR enhancement per shot. Likewise, I can define RS, which is just this ratio of the root T maximum. So VY over root T divided by the maximum of that for Ramsey. And so this is the SNR enhancement in the case where idle time is negligible. It's sort of the SNR enhancement per evolution time that I know about. Right? So what do? Well, we take advantage of the fact that we know how the decoherence happens. So this is a block vector. It's being prepared in the XZ plane. I apologize. This should say VX here. And just allowed to evolve. No detuning, no control, no nothing. You get two types of decoherence on this. You get dephasing, which is destroying all this XY plane information. It's basically random rotations about the Z-axis, is how we like to think about it. Just shrinks the vector back to the Z-axis. And you have relaxation, which takes it to the thermal state. And for now, I'm going to assume we're in the low temperature limit, which means the thermal state is the ground state. So you have this thing taking you to the ground state. You're losing information on X and Y because you sort of got the Z-axis dephasing, and the relaxation also does the same thing. But because it's going deterministically to the ground state, you're actually gaining information in Z. Now, that information has nothing to do with anything else that's happening to it. It's not really going to be changed by, say, delta, the detuning that's going to show up. But it's there nonetheless. We know that it's happening. So now let's talk about what you can do if you add control. So these are the block equations. I'm going to assume that I always start with my block vector in the XZ plane. I'll just define my coordinates so that that is true. Okay, I can always rotate my XY axes however I like. And I'm going to have a control, which is HX sigma X, HY sigma Y, HZ sigma Z. Okay. So these are the block equations. You got the time derivatives of each component given by these decoherence terms. So, shrinking at a rate Vx over T2, Vy over T2, or 1 minus Vz over T1. If you weren't at zero temperature, this 1 would just be replaced by whatever the equilibrium population of Vz is. So infinite temperature, this would be 0. Zero temperature, this is 1. Finite temperature, it's somewhere between. Then you have rotations, which basically look like a cross product on the block sphere. You get rotation about the Z-axis at a rate delta, this detuning we're trying to detect, plus whatever your Hamiltonian control is, 2h3. The Vx grows shrinks proportional to Vy at that rate. Vy grows proportional to Vx at that rate. And likewise, you can have a y-axis control, which rotates Z and X, and an x-axis control, which rotates Y and Z. Now, looking at these equations, we can already say, okay, if my goal was to get the strongest dependence of Vy on delta, I want Vy to change as much as possible when delta changes. Because Vy is the thing I measure, delta is the thing I actually want to know about. Well, the only term that shows up is right here. And it shows up proportional to Vx. So what this tells me is that if I can keep Vx large, then I can make it so that this dependence is as strong as possible. Now, the Ramsey sequence does this in a very, intuitive way. It says, let me start with Vx equals 1, the largest it can possibly be, and just let it go from there. But there's sort of a tortoise and the hare kind of situation here. Just because you're starting out with the fastest possible dependence doesn't mean that's actually going to get you where you're going faster. To do that, we're going to use this protocol that Damidar derived along with student Sarov called coherence stabilization. Now, I want to caveat this, saying that this is almost certainly not optimal for what we're trying to do. It's just good. This was basically a toy model that he originally derived for his open quantum systems class. And then student Sarov went and said, hey, I can generalize this. And we were just going to go and do the experimental demonstration just to show, like, hey, it works. And then we noticed the sensing thing. So while I explain this, do not have it in your head that this is like the best way to do sensing, but this is a better way to do sensing. The idea here is, let's say we're staying in the XC plane, and we want to preserve just the X component. We're going to not care about the Z component. What we can do is use a predetermined drive on Y. This is basically the Hamiltonian as a function of time, the Y component of the Hamiltonian as a function of time here, to rotate Z into X exactly as fast as the decoherence is destroying X. And so exactly cancel out the effect of this decoherence. And so what you see is that X stays constant, completely constant. Now, Z this whole time is decaying. You get decay, but you're also just coherently rotating it into X. And at some point, you lose it, it goes down to 0, and we call that breakdown. Because at that point, there's basically nothing you can do, and you can no longer stabilize X. Now, depending on the initial state, so the initial Bloch vector here, it was like initial X component was 0.9602, whatever. And depending on the ratio of the relaxation time, T1, and the decoherence time, T2, this breakdown time can be very, very short. It can be very, very long. It can even be infinite. So for instance, if I have a slightly smaller value of Vx, I just want to make clear the horizontal scale here, this was 7 microseconds in this simulation. Here it's 100 microseconds. We just started with a slightly smaller value of Vx. The T1 and T2 are the same. And now we can preserve it for much, much longer. You can see this is starting to go to 0 and the control is starting to blow up. That's breakdown. But if we start small enough, actually, you can stabilize forever. It just will go forever. And this is basically making use of that fact that I mentioned before, which is that when it relaxes to the ground state. And we know where that is. So all we're doing is just numerically solving the Bloch equations to figure out what control drive we should be using to stabilize this thing. It's very straightforward. We're just going to only use a drive on the y-axis because we're just trying to stabilize X and Z. So your Bloch equations look like this. You have a detuning Y drive, only a detuning affecting Y, and only a Y drive affecting Z. In the limit where the detuning is really small, it's not going to affect the dynamics of X very much. So we're going to ignore it. And we're going to say that we can basically stabilize X just by setting HY here so that it exactly cancels out this term. And in that case, Vx dot will be approximately 0. Very easy to solve. Turns out you then have to solve for Vz of t in order to get it correctly, but it's doable. And it works as long as Vz is not 0. When Vz goes to 0, this blows up. So mathematically, what it looks like is your drive diverges. Physically, what it looks like is you're trying to rotate Z into X, and there's no Z, so there's nothing you can do. But that stabilization can happen forever as long as Z is kind of growing faster than you're trying to rotate it into X. And the limit on this is just that the Vx you're trying to stabilize is less than or equal to 1/2 root T2 over T1. So basically, the shorter T1 is, the more you're dominated by relaxation compared to dephasing, the more you can stabilize. And again, it kind of makes sense from this information perspective. The shorter T1 is, the more of my block vector is just being quickly transferred to the ground state. And I know where that is and I can bring it back. In general, if Vx is larger than that limit, there's going to be a breakdown time Td. And that's, again, going to be some function of the initial state, the ratio of T1 over T2, and then it's just going to scale with T2. So T2 sets the time scale. The ratio of T1 over T2 sort of sets how long you can do it in units of T2, along with what state you're trying to stabilize. Now, this does actually work. This is now experimental data. So what I'm showing here is tomography data showing the X, Y, and Z components of the block vector measured on a transmon qubit in my lab as a function of time. Here, starting with Vx about 0.65 or so. In this case, there was a breakdown. So we were able to stabilize it for maybe 150 microseconds. By the way, T2 was only like 70 microseconds. And then at this point, Vz went to 0. If we kept the control on at that point, Vz would actually go past 0, and we'd start rotating Vx the other way into it, and that would be bad. So when it breaks down, all we do is we just turn off the control. We just set it to 0. So at that point, you get this T2 decay, this nice exponential decay, like you would for any kind of free evolution, and T1 decay of the Z component going to the ground state. On the other hand, if we started a little bit smaller Vx, just down to 0.6, now it's just stable forever. You can see Vz is going to kind of saturate here. Still it works. But it's worth asking, since I was talking about detuning and sensing all this time, what happens when there's detuning? So this is not quite the small delta limit. This is the sort of moderate delta limit, but it's just here to show you. This is the evolution of the Y component. When I start in the XZ plane, either with my stabilized protocol, in this case, the stabilized states are starting with the two states shown here. So it's like 0.65 and 0.6. Or with the Ramsey protocol, where I start with just Vx equals 1. And what you can see is that the Ramsey protocol, it starts growing faster originally, because Vx is larger. Likewise over here, it's growing faster. But Vx shrinks, and eventually it turns around and comes back. Whereas with the stabilized ones, we're keeping Vx large for longer. And so you can get to a higher maximum. Now, nominally, we actually should have gotten higher over here than we did over here. These were taken on different days, and T2 was just shorter on this one, so the overall signal is just going to be less. But the point I want to make is just that the stabilized signal is larger than the Ramsey, meaning there must be some advantage here. We're more sensitive. So then we ask, okay, how much more sensitive? Turns out the analytical theory on this is not too bad. There's a Mathematica notebook posted on our GitHub that you can run through. I hope I did a good job explaining it. It's really not that bad. Let's say we're going for one of these states where there's no breakdown. So we just maximize the value of Vx that we can stabilize forever. Well, you can solve for that value of Vx. Again, it was just this 1/2 root T2 over T1. And in the small delta limit, Vy is just going to be delta T2 times that Vx. So you multiply through, you get this quantity here, and then, okay, you can divide that by what you would have gotten for Ramsey to get this RV, this SNR improvement ratio per shot, sort of the signal improvement ratio. It's E over 2 root T2 over T1. Well, E over 2 is about 1.3, 1.35. Root T2 over T1 can be as large as root 2, 1.4. So this quantity can actually be as large as E over root 2, which is 1.92. So almost a factor of 2 improvement in signal. That is, by the way, if you were just trying to get that by averaging more, that's almost a factor of 4 in averaging. So this can be quite significant. Now, this was just for the case of trying to maximize Vy, not Vy over root t. And there was this, difference here where the Ramsey was growing faster. So it reached its maximum earlier. So maybe, maybe we're not winning that way. And it turns out with these sort of long-time stable states, we're probably not. But for states with a breakdown, we can do a little better. Now, what it looks like is this. Vx is going to be stabilized for some length of time in this breakdown and starts to shrink. This whole time is rotating into Vy. And it's a little subtle here, but this blue arrow that's Vy, you'll notice that it actually keeps growing a little bit after the breakdown. It goes just a little bit longer. So using a state with a breakdown, you can make the growth happen faster, but then it can still keep growing for a little while after this breakdown. Very easy to solve for this. Before breakdown, you basically make the assumption that Vx is constant, and that equation I would feel confident assigning to any freshman. This is the evolution. It just grows exponentially, basically, or saturates exponentially. After breakdown, it just decays exponentially and rotates the way it did before. Here it's just rotating times the time since breakdown, decaying with the time since breakdown, and starting at some value that was just whatever Vy was at the breakdown time. Now, the one thing I haven't done here is shown you the breakdown time. There is an analytical expression for it. It will take up most of this page. So I didn't write it. You can solve analytically for that. You can also solve analytically for the time that maximizes either Vy or Vy over root t in this limit after breakdown. That's pretty straightforward. What you can't do is then solve for the value of Vx naught, the initial state that maximizes everything. You have to just sweep over Vx naughts and see what happens. So we do that. On the right here, these are the times that are maximizing. So red on the right, time that maximizes Vy, time that maximizes Vy over root t in units of T2. T2 just sets the time scale for everything. And you can see basically as T1 gets longer and longer compared to T2, in other words, as relaxation becomes less and less important, this time is going to eventually saturate to the Ramsey value. In this case, it saturates to 0.5. In this case, it actually doesn't. It saturates to just under twice T2. Turns out you can just always do better than Ramsey. In black on the left here, this is theta max. This is the polar angle of the initial state. We're just going to say our initial state has a Vx of sine theta. In units of pi, you can just see it kind of has a nice dependence here. We can solve for it numerically. What this gives us is these ratios, RV and RS. Remember the SNR improvement with fixed shots, SNR improvement with fixed evolution time. And as a function of this T1 over T2 ratio and the initial state angle, we can find a place where we maximize. Now, this dashed black line, that's 1. Anything above that is an improvement. So it can actually get quite large. In these sort of like straight line regions, that's when it was a stable state. Everything just scales linearly with Vx. Above that, it starts to be unstable. The RV can be improved a little bit more, up to 1.96, when you use a slightly unstable state, a state that has a breakdown. RS can get quite a bit better, 1.18. The best we could do before was like 1.03. So really significant improvements here, and more importantly, we can do this for sort of all T1s over T2s and find that it just stays above 1 the entire time. So here's RV, here's RS, both as a function of T1 over T2. They get smaller as relaxation becomes less important, but they always stay above 1. These colored plots are just versus T1 over T2 and versus initial state. This is kind of a sweep we have to do to pick out these data points. But I want to note that the markers here are numerical simulations based on sort of exactly solving everything, whereas the dashed line is doing these semi-analytical solutions where we're always taking these limits of small delta, and it really matches up quite well. So it works with this. All right, does it actually work? Yes. This is now experimental data. These dashed lines here are not fits. These are predictions. We measured the T1 over T2 ratio, and this device was about 0.8. Generate those dashed curves. That's the only thing we do. The markers here are basically us going and measuring Vy for both Ramsey and stabilized experiments while varying delta. We deliberately change the decay. And then we go and we fit the slope. The error bars here are 1 standard deviation of us doing this many, many times. You can see it agrees pretty well with the theory. And importantly, it goes above 1 for a reasonable range of parameters. Now, this is actually not obvious that this would have happened because, among other things, T1 and T2 change in this device, in most devices. They're not fully constant. In superconducting qubits, it's pretty characteristic for these to have noise of maybe 25% or so. Turns out they tend to be fairly correlated. So the noise of the ratio is actually only about 10% in this device. But there's still, there's noise there. So it worked, even though it was sort of a drifty, noisy device. Now we can characterize how bad that is, how robust it is to these things. Easiest to do it numerically. At this point, I just took this from the paper because I was proud of this caption. It ended up being the best caption I could write. These ratios, again, these improvement ratios, RV and RS. Once again, this is improvement in signal only in Vy. This is improvement in Vy over root T. White here is defined as what improvement you would get if you were perfectly calibrated at T1 over T2 goes 1. So T1 is T2. Then what we did is we said, okay, your control is going to stay the same. You're going to control the thing exactly the same way, with the same Hamiltonian waveform. You're going to measure at exactly the same time. You're going to measure at the time that you thought would give you the best value. But we're going to go into the back end and change T1 or change T2. And we'll do this for both your coherence stabilized protocol and the Ramsey protocol, comparing them on equal footing. And the question is, okay, what happens to RV? What happens to RS? Well, there's definitely dependence here. It gets worse as you go to the top left. This is when sort of decoherence is getting faster while relaxation is getting slower. So T2 is getting shorter, T1 is getting larger. But most of that dependence here is not really a miscalibration dependence. It's just the fact that the protocol just doesn't work as well in that circumstance, even if you're perfectly calibrated. And you can see that based on the fact that along these sort of diagonal lines this way, it's actually pretty constant. These are lines of constant T1 over T2 ratio. And as long as that ratio doesn't change, you're actually doing quite well. Now, it's not perfect. You can see there's a little bit of curvature here in these lines. So there is a little bit of dependence on miscalibration, but it's very weak. It's really just a dependence on how well could this have worked in the first place. So it's kind of nice. It's very robust. And you can actually sort of see that. I go back. So for instance, these curves, they've got a reasonably flat region on top. These measurement times aren't super steep. If I went to this data, you can see there's a reasonably large maximum here. where I could measure. So it's not that sensitive. You get a nice little sort of local maximum. So those are our results so far. Just summarize it. We're enhancing SNR, we're doing it unconditionally. There's no situation in which this is worse than Ramsey, because this protocol basically encompasses Ramsey. All you do is you start with Vx equals 1, your breakdown time happens at 0, and you've done a Ramsey sequence. I really want to emphasize, nothing here is extra. If you can do a Ramsey sequence, you can do this measurement. Because it only requires the same control that was used to prepare and read out your states in the first place. So there's no feedback, there's no auxiliary systems, there's no ancillas, there's no extra entanglement. You don't need to change your sensor at all. Should work for any sensor. Now, it works best when it's relaxation limited, and I didn't really go into it, but it also works best when temperature is low, because again, you get this deterministic resetting to the ground state. How much that advantage is might actually be worth making things worse to create those conditions. There's ways to sort of engineer dissipation into a system and make it colder and more lossy. Now, that's definitely not going to help Ramsey. That's all, it's just going to shorten T2. It does help this protocol, but usually not relative to doing nothing. I checked briefly. However, that can often have other advantages. Like it can shorten your idle time because you're resetting the system faster. Or maybe it like gives you a better readout or something. So it's worth kind of exploring that. Is it worth making things worse to make them better? Now, going forward, we want to actually optimize this. There is a very, very clear proof that what we are doing is not optimal, which is this. We let the system evolve to breakdown time. Then we let it evolve a little bit more under no control, and then we measure. Well, during that time, it was relaxing somewhat to the ground state. We were picking up some VZ. There was this extra coherence there that we didn't use. We could have used that. So like a really, really simple improvement to our protocol is just at that time, just rotate whatever that VZ is back into VX. You get just a little bit more boost. Now, that's not a huge improvement usually, but it's not zero. And we're quite certain that if we actually did optimal control, we could do a lot better. It has to be done numerically. I spent about a week and a half trying to do analytical optimization of this. Anybody familiar with the Poitras principle? It's very powerful as long as you have constraints. But this is actually a really, really poorly constrained problem because I am allowed to vary the initial state, the final time, and the control the entire way. And the only thing I care about is the final state. There's like no cost function except for that. So it turns out that it's just so poorly constrained that you just get this enormous mess of equations. On the other hand, you can throw a gradient descent algorithm at it, and it works pretty well. I want to apply this now to time varying signals. I was looking at delta being constant. What if delta is oscillatory? There's one very straightforward technique that comes to mind, which is just that I just oscillate what state I'm trying to stabilize. So if I was trying to stabilize Vx over here, well, the detuning is rotating it this way, it's starting to rotate there. When the detuning switches side, it would rotate back. Well, okay, I stabilize Vx over here until it's done rotating, then I flip it over, and it starts rotating the other way, which goes this way. And so it keeps picking up. Now, that's kind of like a bang-bang, like a dynamical decoupling type of approach. It's probably actually going to be better, again, to do it kind of continuously. Because if your signal is oscillatory, it's going to spend some time being small. And while your signal is small, maybe you just want to hang out on the z-axis when you're not as vulnerable to decoherence. Now, there are all these other zoo of techniques that often require extra resources, but have been implemented and are implementable, for instance, in a superconducting qubit. And we should be able to combine all of these things and see how far we can push. One very straightforward thing would be to use these adaptive phase estimation protocols, which allow really good detection of very large signals, without saturating the detector, to start from some large unknown signal and very, very quickly hone in on it, and then use this stabilization protocol to get the fine resolution. Should be straightforward. All right. That's all I've got. Thank you for your attention. I'll take whatever questions you got.
Yeah, I'll start. So thanks for the nice talk. There is a general theory that we worked out of time-dependent with quantum metrology. I don't know if you're familiar with this set of work, but that would seem to be the.
I think I read it and didn't understand it, but
Okay.
that was several years ago, and maybe I'm better equipped to understand it now.
You can apply that here and find your optimal controls, I think, in a very straightforward way.
Yeah, certainly. I mean, there's. I'll certainly look at that. We have a code from Christian Koch,
Yeah.
who has a nice thing for doing this in this sort of static signal regime, and we're going to try to adapt that, but maybe it's better to just go straight to this optimal theory.
Yeah.
But there's a whole zoo of optimal control methods, and
I guess it depends on what the goal is, but it seems like your goal is the metrological goal, right? You want to estimate this delta as best you can.
Yeah.
If that's what you want, then you need to do optimal metrology.
mm-hmm. Yeah.
And the other comment I would make is that I think while maybe this technique you talked about adapting your control time dependently so that you maintain your coherence, well, that may indeed be better if you degrade your coherence, right? If you worsen your coherence, I would be extremely surprised if the optimal solution did better if you had worsening conditions. Right?
Oh yeah, I don't think there's any circumstance under which, only considering the qubit evolution or the sensor evolution, you do better by worsening coherence. I think there's probably a way to prove that you can't do that. However, if it brings you other benefits, such as giving you better readout fidelity or giving you a shorter reset time, then it might be worth it.
Yeah, I'm saying I'm skeptical of that statement too.
I mean, this is one of the issues we run into with qubit readout, is that the optimal design for superconducting qubit readout, it's really hard to prevent Purcell limits. We do our best with filtering and everything, but we still can run into these Purcell limits. Maybe that's actually not such a big deal if you can get a better readout. It's going to depend on the sensor. Something I didn't mention on any of this is there was a prefactor to all of this SNR, just some constant factor between 0 and 1, which represents state preparation and measurement errors. And I sort of inherently made the assumption that was going to be the same regardless of what my protocol was, so I got to ignore it because I was only taking ratios. Maybe it's not the same. Maybe you can get some win there.
Other questions?
So this is a genuine, I haven't really understood this in this project before. It's like, so from what I understand, you're kind of picking out a certain value of the Y block coordinate for comparison and defining your SNR in terms of this maximal value for sensing.
So the SNR just is the SNR, but I'm defining these SNR ratios of the NRS in terms of how good is my SNR in this protocol compared to how good would it be for a Ramsey protocol.
I guess my question is, like, if the goal is to improve how well you can sense delta itself, that delta would be found not through a single point, but through some sort of fit of the entire curve, right?
Well, that's the thing. You can do it with a single point. If delta is large and you're getting oscillations, then you definitely can't do it, because if you don't know how large it is, you don't know where on the oscillation you are.
Oh, so.
But if delta is
Oh,
guaranteed
okay.
to be small, your signal actually just becomes linearly proportional to delta. And the only other things it depends on are parameters of your sensor. So if you know those parameters, you can get it.
I see. So in some ways that point that's the maximum, it almost serves as a as you could equate it to a prefactor kind of scaling the whole curve up or down. And so it really is equivalent to considering the curve as a whole, as opposed to, because it just seems like the noise in your calibration of delta would be a lot greater by picking out a point versus looking at.
Oh, certainly. I mean, the more points you look at, the more confident you're going to be. But that's true of any protocol. And the point here is that sort of per maximal SNR point, you're doing the best. You can kind of see in these equations, so like before breakdown, everything's proportional to delta. So whatever Vy is at breakdown is going to be proportional to delta. And then the growth later is also proportional to delta. So a factor of delta just comes out in front here. This whole thing just becomes linearly proportional. And the only other things it depends on are like the breakdown time, we know that. The initial point, we know that. The T2, we assume that we can know that reasonably well. And there is this question of like, you know, what's the best way to handle T2 fluctuations? But that's a situation you kind of run into identically with the Ramsey protocol. You know, one way to handle it is just to take a bunch of points on a curve and fit it. But you know, the larger those points are, the more likely you are to get the right answer.
Any questions?
Funny question. What if your noise is non-Markovian? So T1 or T2 exponential decay isn't quite good enough.
So this taking the sort of ultimate non-Markovian limit, there's nothing you can do because your noise is your signal. You know, your noise is a constant offset of delta. So how do you tell the difference between that and the actual delta? The only thing you can do is try to get it to go away. Now, if delta was at some higher frequency, great. Then we can use some kind of dynamical decoupling like technique to lock in on it. But if delta is guaranteed to be at zero frequency, there's no way to get away from the zero frequency noise.
So 1 over F noise is a problem.
1 over F noise is a problem if you're not allowed to move your signal frequency, which is why, yeah, if there's like one like goal that you could ascribe to all of experimental physics, it's like find ways to put your signal at a particular frequency that you know ahead of time, that it's not zero. Like we were trying to design a gravity experiment when I was a postdoc that was going to have a frequency of 1 over 24 hours. So it was going to depend on like whether we were facing the sun or not facing the sun. And that was going to be better than having a frequency of 0, because we'd at least be able to actually see it change compared to just fluctuating.
Still very hard though.
Yeah. Turns out that's a very long period. So quite far into the loop. That was not actually the biggest problem with that experiment. The biggest problem was that it was going to require a centicurie source, which for anyone who knows about radiation is sort of face melting kind of. Yeah.
Any questions from the Zoom?
I have a question.
Yeah.
So your protocol requires knowledge of the Z component of your block vector. How are you getting this information during
Well,
the
we're
protocol?
assuming that when we prepare a state, we prepare it with reasonable fidelity. So we know the initial state.
Okay.
And then we're assuming also that we know the coherence times at the sensor, that we know T1 and T2. So we know on average how the block vectors evolve.
I see. So it's an analytical calculation. This is the difficult optimization problem that you were mentioning.
Yeah, I mean, there's this question of like how to handle it if you don't know these things ahead of time. And what I've assumed here is like you have done some completely separate measurement to calibrate T1 and T2, and you have them reasonably well calibrated.
I see. Okay.
What I haven't talked about is like, can you also use a technique like this to better calibrate T1 and T2? And my thought is probably, but we haven't looked into it.
And you would just do metrology, treating those as unknown parameter. As you take data, you find your knowledge.
The question is whether something like Ramsey or typical T1 sequence is already optimal. I think it probably is, because in those cases, you're looking for the rate itself.
But then you would just do 3-parameter estimation, right? You see if you saturate your camera.
Yeah. But I think I can kind of quickly claim, just based on these equations, that if I want to know these things, the only way I can pick them up is by their changes on these coordinates, and there's no cross term there. You know, the Vy part depends on Vy. And so I'm always just best making each individual component as large as possible, which is what you do in the Ramsey and T1 sequences.
All right, if no further questions, let's thank Eli again.